most engineering deals heavily with math and the physical sciences, but biomedical engineering in particular really brings in the biological sciences as well.
So how can we use our knowledge of engineering, math, physics to improve the outcome of therapies? How can we get people back to their daily lives?
It's the one engineering discipline that really encompasses electrical, mechanical, chemical engineering, materials engineering, nanotechnology. It really embraces all of that. And there's not one single engineering field that you cannot find within biomedical engineering.
We in biomedical engineering can work in the area of medical devices, or we can work in the area of research.
Biomedical engineering is a relatively new field. It's not one of the traditional engineering fields.
One of the reasons why biomedical engineering has evolved into its own particular discipline is because there's a tremendous need on the part of clinicians to be able to interact with people who are knowledgeable not just about engineering, but are knowledgeable of the medical and biological aspects of the problem they're trying to solve.
In the OR of today, you really can't see the physician. All you see is technology around the physician, and that's what's unique about biomedical engineering, is that it's embedded in the clinical space.
As if we train biomedical engineers and they're ready to hit the ground running, it's a much easier collaboration. They can work on more significant problems, and we can solve problems much more rapidly.
Basic research in bioengineering, by and large, has focused on is understanding the underlying pathological mechanisms, so the underlying cause for a disease or the underlying cause for something something going bad in an organ or tissue.
There's just so many possibilities and technologies now that are available to study the biology and the engineering of living systems.
There are people that are working in rehabilitation engineering. There are people that are working in implants and biomaterials. There are people that are interested in a whole variety of issues.
So the ideal solution that's conceptualized by the basic research investigators may not exist. So they're trying to get there, while the folks who design products are saying, what can I do with what I have, and what is the best solution I can deliver to the patient?
And there's so many potentials in basically any area you can think of to make progress.
How do you solve it with what you have today?
One of the things that we're currently working on is repair and replacement of the anterior cruciate ligament. The issue is once you've damaged the ACL and you've had it reconstructed, you have really good short-term outcome. But if you look at 10 to 15 years out, that number drops significantly because they start developing osteoarthritis. And the only current therapy to correct it is a total joint replacement. And that's where we cut off the bottom part of your thigh bone and the top part of your tibia, put in two metal parts and a piece of plastic. That's the only way to repair it. So the goal is to find a better way to repair and replace the anterior cruciate ligament, so the next generation, we're getting ACL reconstructions even younger and younger, don't have this problem.
What we do here is we use an industrial scale robot to manipulate the joint. In the case of the ACL, we can run an intact motion. We can then run a deficient motion where we have severed the ACL, and then we can go in and actually perform a surgical reconstruction on this joint here. And then once we've reconnected it, we can run it again and see if the forces are back to the intact condition.
So what we're hoping to do with some of our work using robotics is to understand the problems that we have after reconstruction. So if we can identify that with our robotics technology, we can then redesign the surgical outcome or redesign the graft that's put in there to try to alleviate those problems. I actually played soccer, and in my junior year I blew out my anterior cruciate ligament.
I was an athlete in high school. I tore an ACL, had to go through a painful surgery to repair that and a long recovery period. And I think, it seems at the time there must be a better way to do this.
I was always interested in engineering because I'm a big math dork, and I really liked math, but I was looking for a way to apply it. I didn't want to do straight mathematics.
I learned that you can do medically relevant research as a PhD. And that was really what I wanted to do. I wanted to do the research side of things to understand how things work, why they work, and how I can improve on them.
So this was really the perfect marriage for me, engineering and biology, to do biomedical engineering.
I think of the STEM fields, the science, technology, engineering, and math, I mean, all of that, biomedical engineering encompasses all of that.
It's really STEM on steroids.
It's not only just about performing experiments, but it's also about the mathematical principles that are used to try and solve some of these problems.
You know, we're doing trigonometry, it's like, this is the rule of cosines. I'm like, okay, well, there's probably some software program that's going to be able to do this for me. Well, not necessarily.
You have to get exposed to the physical sciences like chemistry and physics.
It's important to understand the interactions between different types of tissues and how they form the materials that ultimately govern the rules of mechanics that we apply.
To design a heart valve, you need to understand Newton's laws. If you want to design a stent, you need to understand Newton's laws.
I've been doing this a long time, and my program is long and it can be grueling, but it definitely is worth it in the end.
So there's a lot of different biomedical engineering programs in the state, but what you need to look at from those areas is what do they specifically focus on.
Programs like the one I'm in here at UC are designed to train medical researchers, essentially, people who can treat patients, but who are also involved in developing the next generation of technologies to treat those patients.
We're more of a mechanics and physics background that we look in, where others might be the electrical components or the chemistry side of things.
I tried to talk to people in my community that I knew were associated with places like the University of Cincinnati or Ohio State University.
Most of our students who finish an undergraduate education will choose one of several different career paths. Some of the very best students that we have will pursue medicine, and so they are really choosing biomedical engineering as a pre-med option.
I landed up actually forming a company here in Cincinnati that specialized in medical device development.
One thing that appeals to me about industry is the fact that you know that you're going to have money to do it, generally.
Others will choose to go and work in the government. So you can work at NIH, you can work at the National Institutes of Standards and Technology, NIST, you can work for the FDA.
You're entering a field to make people's lives better.
And the more you get into it, the more you realize there's just so much potential here.
That's what I find interesting, is that humanitarian side of biomedical engineering is trying to improve life.
Every day I think to myself, tomorrow could be that day when I do the experiment that's gonna, uncover something that no one else has ever known before.